So in this video, we'll learn how to synthesize primary amines. Specifically, we'll be doing ones that don't add carbons, like our nitrile synthesis did, but we'll be using first what's called the azide synthesis. In this reaction, we're going to take an alkyl halide, treat it with a source of azide, typically sodium azide, same thing in your airbags for your own information. We'll do an SN2 type reaction there, replacing our halide with the azide, and then we will do some sort of reduction, either using hydrogen or lithium aluminum hydride. We will get our amine out. We'll take a look at the mechanism here. The reduction steps here, again, you have a couple of options depending on what else is in your molecule. So hydrogen and some catalyst will reduce your azide into an amine, or you can do lithium aluminum hydride, and then water will take care of your reduction. Either one. You can use either of these pathways. If we want to look at the mechanism, azide as a Lewis structure looks like the following. Let me cut the other two here. So azide has overall 2 minuses 1 plus, giving it -1 overall. It's going to go ahead and find our alkyl halide. Here, let's say we're using 1,2,3 propyl bromide. We're going to go ahead and attack it, kicking out the bromine, much like any SN2 reaction would do. We're looking at only primary and secondary substrates. Since this is SN2, we're looking also at inversion of stereochemistry. We'll end up with 1, 2, 3, 4, too many carbons here. We have our nitrogens everywhere. And if we now include our reducing agent, let's say we're using lithium aluminum hydride. So we're looking at hydride as our reduction source. We're going to go ahead and have our hydride attack our nitrogen. It's going to go ahead and bonk some electron density onto our middle nitrogen, the one that's positively charged. We will now have a hydrogen on there, and we have our negative nitrogen ready to go. Anytime, sorry, too many lines there. Anytime that we have all these nitrogens together, we've seen this before with the diazoniums, we have that capacity to lose it. And indeed, we will see that that will happen next. Whenever you have 2 nitrogens that are kind of ready to go, you're going to lose them as nitrogen gas. We're going to form a triple bond between 2 nitrogens, and that nitrogen gas is going to go away. This is irreversible. So generally, I mean, these are technically reversible steps, but we don't see them very often as reversible. The nitrogen one absolutely is, the nitrogen gas one is absolutely irreversible. We're left with the following. Now, this is a very strong base. That's going to go ahead and find our water now, which is introduced in the second step, because water would react with our lithium aluminum hydride. Remember, we're going through this separately. That's going to end up giving us our amine. We'll have our NH2, and we'll lose some hydroxide. We don't want to put acid with this because, as we know, amines are basic. So if we try to wash this with acid instead, we'll end up protonating our amines. We don't want that. So suffice it to say, in our nutshell, treat your alkyl halide with sodium azide and some sort of polar aprotic solvent. Go ahead and introduce some reducing agent, either hydrogen gas and a catalyst, or lithium aluminum hydride water. You'll end up getting your amine out. That's one way. The other way, also on alkyl halides, generally primary, maybe secondary, another SN2 type reaction is called the Gabriel synthesis. And it also acts on alkyl halides. So we have this compound called phthalimide, which when treated with hydroxide, say potassium hydroxide, turns into, same thing minus that hydrogen there. Remember we saw amides are slightly acidic. We have now 2 amides, so it's extra acidic. That's why we can do this, so we'll be able to take off that hydrogen. This is really the reagent that we're going to use, and it's going to be our nitrogen source. So we're going to go ahead and take our alkyl halide of choice. Say we have that same one, the propyl bromide, which I will draw the same way as before, so that we can have the substitution happening nicely here. We're going to go ahead and kick out our bromine, which gives us now the nitrogen attached to that. I'm going to just copy paste it here. So we have now our 3 carbons attached. 1, 2, 3. We've lost our bromide ion, which is ideal. We've found potassium bromide. Hooray. We now have to just kick out that nitrogen-containing bit. Best way to do this is using hydrazine. If you use hydrazines on this, you will end up doing 2 acyl substitution reactions, forming the following byproduct, plus your amine. 1, 2, 3 carbons. So again, it works on alkyl chlorides. So this is our substrate here, our alkyl chloride. Alkyl halide. That was a bromine. Wow. Using this phthalimide and the presence of base, followed by hydrazine. So generally speaking, we might see this as the following. You will either see your phthalimide as the kind of starting reactant, and say you'll treat that with KOH first. You'll add in your alkyl halide of choice. We'll just say RX for now. And then step 3, hydrazine. Is that the way I've written it before? Either way, you can write hydrazine either way, NH2, NH2, or H2N, NH2. They're the same. And you'll end up now getting your amine out. This one also does not add any carbons. However, as we see, we have some terrible atom economy here. We are using this phthalimide, many atoms just to get 1 atom out of it. Kind of terrible. But it works. These reactions, though, have the following conditions. These reactions make only primary amines. And the substrates must be primary or secondary alkyl halides. And of course, it doesn't necessarily have to be an alkyl halide, anything with a leaving group. So if you have a tosylate, this will work, either of these. Anything you can do an SN2 on, you can do these either the Gabriel or the azide on. And again, you can do the nitrile synthesis too, but remember that will always give you 1 extra carbon. So the number of carbons here is the same. From start to finish in your alkyl halide and your final product, the amine. So problem though, the biggest problem with this is that we can only make primary amines. How do we make secondary amines or tertiary amines? Well, you'll have to watch the next video to find out.